So in the last video, we were able to derive this molecular orbital diagram for diatomic oxygen. And remember how we did that? We had the different atomic orbitals of oxygen. Of course, first we got the point group, which is D infinity H. And then we combined the atomic orbitals using atomic orbitals that had the same symmetry and similar energy. In this case, since they're the same atoms that have the same energy, in constructive ways and deconstructive ways to make bonding and anti-bonding molecular orbitals respectively. We populated with electrons and we got out the bond order. And we had to, and very importantly, was come up with the symmetry of these different molecular orbitals kind of from scratch. We had to think about how these orbitals would transform in the point group of the molecule. The nice thing about molecular orbital theory is that once you have one MO diagram done, then you can look at isoelectronic species very easily. And so we're going to do that in a little bit. But first, I just wanted to bring up this idea of mixing of molecular orbitals. So if you have molecular orbitals of the same symmetry and similar energy, they will also mix with one another, just in the same way that you have two atomic orbitals of similar energy and same symmetry. They will mix to make molecular orbitals. Two different molecular orbitals of the same energy and of the similar energy and same symmetry can also further mix, okay? And so if you look at our MO diagram, and now we're going to be looking at, again, not only isoelectronic species, but also kind of any diatomic molecule with second row elements, right? So we can look at fluorine or diatomic neon, which of course is not a stable species and doesn't exist. But anyway, what you can do is, if we look carefully at this, you'll notice that, hey, in our MO diagram, I've just taken this slide that we started with, and I just cut out this bottom portion with the 1s orbitals. And why did I do that? Because the 1s orbitals here, again, are core electrons. They don't really participate in bonding, right? So I just reproduced that slide here. And one thing you'll notice is that, hey, we have 3 sigma G plus and 2 sigma G plus. Those orbitals are of the same symmetry. And so they're going to mix. Now, the extent to which they mix depends upon how close they are in energy. And so for oxygen, fluorine, and neon, these diatomic molecules of those elements, the energy difference between these orbitals is quite large. And so there is mixing, but it's relatively little. Why am I saying it's quite large? How would I know that? I know that from this chart and this principle that we said earlier, where basically we're looking at the energy difference between the 2p and 2s. Well, not strictly, right? We're looking at the energies of these molecular orbitals, but the energies of the 3 sigma G molecular orbital and the 2 sigma G molecular orbital depend upon the energy of the atomic orbitals that they start with. The atomic orbitals that they start with are the 2p and the 2s. And so the 2p orbital is here, and it had to go down in energy when it formed 3 sigma G plus, right? So whatever the 3 sigma G plus energy is, it's lower than the 2p from which it started. And whatever the 2 sigma G plus energy is, it's lower than the 2s energy from which it started. And so what you can see, right, is for reasons we talked about in an earlier video, when you have more protons, higher atomic number, the energy of the atomic orbitals will decrease, becomes increasingly stabilized. And in particular, right, the gap between two atomic orbitals increases as you increase the atomic number. In other words, we said that the slope of the more core-like atomic orbitals was greater because more core-like atomic orbitals are closer to the nucleus, so they feel this electrostatic influence greater, right? And so if you look at the gap between the 2s and the 2p, you can see for neon and fluorine and oxygen, it's very big. That means that it's a very big difference between 3 sigma G plus and the 2 sigma G plus, because it came from the 2p and 2s orbitals. So all that's to say is that this is why oxygen, fluorine, and neon, there's not a lot of mixing between 3 sigma G plus and the 2 sigma G plus. There's a large energy difference, although they do have the same symmetry, and there will be some mixing because they have the same symmetry. Because there's a large energy difference, there's not going to be a lot of mixing. Not enough to significantly perturb the molecular orbital diagram. Look at the case for boron, 2p and 2s, carbon, and nitrogen, much closer in energy, okay? And when that happens, now you have 2 molecular orbitals, 2 sigma G plus, 3 sigma G plus, of the same symmetry that are pretty similar in energy. And because of that, you're going to get mixing. And you're going to get significant mixing and enough mixing to actually change the energy ordering of the molecular orbitals. And so now I'm just showing the molecular orbital diagrams. I've got rid of the left and the right-hand sides, the atomic orbitals from which these molecular orbitals came. And so, you know, I'm interested in these 2 sigma G plus and 3 sigma G plus for these less heavier elements. You're going to get significant mixing because they're more similar in energy. And so it turns out that the energies are significant enough, the mixing significant enough that you actually have a change in the ordering of the energies. So what's going to happen? You're going to add, you're going to mix, right? Constructively, the 2 sigma G plus molecular orbital and the 3 sigma G plus orbital to make this interaction. And I'll go over how that works in a second, but that's going to stabilize pictorially. That's going to stabilize, make it further bonding, okay? And so that's going to go down in energy. Anytime you mix things, whether it be atomic orbitals or molecular orbitals, you're going to make one that's stabilized in energy and one that's destabilized in energy. And this is going to make kind of the destructive mixing, and it's going to become more anti-bond. It's going to become more anti-bonding in nature, a little bit more anti-bonding in nature. It's overall still bonding. You can see there's a bonding interaction there. Again, we'll talk about that in a second, how you draw these pictures and determine, you know, how much anti-bonding and bonding character there is. But the key thing here is that there's actually enough of a change in energy that the sigma G plus, here, the 3 sigma G plus, rises above the energy of the 1 pi u. Now, how do you know how much this rises in energy? You don't. Group theory can't tell you the magnitude of most changes, okay? It can give you relatives, right? But how do you know if this is going to cross over? You don't. And you need to do quantum mechanical calculations, i.e. computational chemistry, to figure that out. All right. But what I'm telling you is that for boron, carbon, and nitrogen, there's enough mixing that there is a switch in the energies. For oxygen, fluorine, and neon, there's not much mixing. And yes, this mixing still occurs, but it doesn't rise up high enough to cause a reversal in the energy ordering. And so this is, you know, how pictorially you would do this. Okay, so we're mixing this 3 sigma G plus formed from these 2 PZ orbitals and the 2 sigma G plus. So we're going to add them constructively, and then we're going to subtract them. What does subtracting them mean? Subtracting them means adding the negative. So you can see here we added the light colored version. Here we added the negative, the dark colored version. And how is that going to work? Right, well, you're adding light colored spheres to light colored p lobes. So that's going to make big p lobes there. And you added white colored spheres to dark colored p lobes. And so that's going to make small p lobes there. Why is that, right? Because these p lobes, the p lobes are more directed, so they're longer and skinnier. And so there's going to be a little bit of, P here that's extending, dark P here that's extending on the end, beyond kind of where the edge of the sphere can extend, right? And so that gives you that little P lobe. But in general, right, that's going to be pretty small because you had some anti-bonding interactions between here and here, right? White and light and dark. Same sort of thing for here when we add the negative, that means we're doing subtraction. When we add the negative, then we're going to get very small lobes here, right? Mostly we had anti-bonding interactions, but there's a little bit that's distending. So we got the small light colored interactions there. And then we made these dark colored lobes very big because we had constructive interference there. So net, you know, in here we still are bonding, but we're less bonding, it's weaker. The anti-bonding portion became stronger. Basically, bonding became less stronger. Here we really increased bonding. And so that's sort of how that works there. That's why you increase bonding here because it's more directional. This went down, and this you decrease bonding is just lower lobes, lower electron density, so that went up. So pictorially, this will always match in that way. So what I just want to say is you might have learned, hopefully you learned this, maybe you learned this, and it was very confusing to me when I learned it in general chemistry. Why there was more mixing? Where did all this come from? Why were the MO diagrams for boron, carbon, and nitrogen different from that of oxygen, fluorine, and neon? Now you can kind of know from a group theory perspective where this comes from. This all comes from quantum mechanics, and it comes from fundamentals. And we're not just kind of just telling you to memorize this, right? Lastly, you can see that we can call this SP character. It's mixing of S's and P's. This is actually mixing. There is a physical basis for this. The wave functions are actually mixing. This isn't like a hybrid orbital concept now, right? Which we talked about how that was basically an artifact that Linus Pauling invented when we're going over VSEPR in the last chapter. This now is actual physical mixing, SP mixing. And you can do quantum mechanical calculations and figure out, how much SP character is in the 3 sigma G bonds there. And if you do that, you can see, there's the 3 sigma G bond is this one. So it's mostly P in character because it came from P orbitals. And you can see that, there's very little S character that would be representative of mixing in fluorine because that's a very heavy element relatively. And so the 2S and the 2P are very far apart, little mixing. But if you go to nitrogen, right, there's significantly more mixing. And obviously, if these calculations were done for boron and carbon, those aren't super stable molecules, which is why they couldn't be done as accurately. It would just be completely theoretical at that point. There are ways from spectroscopy to get these numbers experimentally, okay? But for boron and carbon, they would be even higher, right? Boron would be the highest. So hopefully this kind of resolves maybe an issue that you had from general chemistry when you learn molecular orbital theories. This is also a good framework for us now to launch into more complicated molecules, going to multiple atoms. So far, we've only done 2 atoms, and things are relatively straightforward when you do 2 atoms, but they get more complicated and beyond what you ever learn in general chemistry when you get to 3 atoms or more.